Hi, I'm Reverend Greg and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. This time we'll look into a Sin City effect shader. As always, a short disclaimer, this tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistakes in my video or see a better way to solve a problem, please add a comment so everyone can learn from you. Now, first let's think about what makes a Sin City effect. Certainly there has to be a grayscale conversion. And it needs high contrasts. There's lots of black and white in Sin City, which gives the movie a comic book feel. And of course a popping color. In most cases it's red. Now we have to understand that a shader won't ever be as good as the artists who decide what stays converted and what gets colored. Even the contrast was decided by artists and may even be different on different regions on the same scene. If you look at some Sin City footage, you'll see very strong contrasts on some parts of an image and normal contrasts on other parts. Also, it's difficult to do this with any other color but red. The code of the shader we're going to look at can be easily changed to pop green or blue instead of red, but the greens and blues as they are defined in RGB are often not as close to the greens and blues we see around us in the real world, not as the reds are. So only rarely the effect works as well as with red. Now we're going to take a different approach in this tutorial. We're not going to create this effect from scratch. We're going to grab a shader from the internet and try to implement it into GMS. So I searched for a Sin City shader effect and didn't find a lot, and what I found was mostly not very convincing except one post on Reddit. I'll leave a link in the description of this video. So this is a solution by Terrifying Cookie in Reddit. As you can see, it's an HLSL shader, not GLSL, but you'll see it's not too different to not understand. He also left an example image, and I think he did a really good job in recreating that Sin City look. And here's the link to his code and paste bin. It might look intimidating at first, but it's mostly comments, which is great for us. So let's copy that text to paste later. Now back in GMS, the usual procedure. Create a new shader and name it Shader Sin City. Next, duplicate the template module in our base project or create a new object. Name it Object Sin City. And place it in our test room on the main layer. In Create Event I set up the usual stuff. Info text. Sprite, and shader. And in draw event we just make sure that the sprite gets drawn by this shader. Now let's open the shader and close the vertex shader. Inside the fragment shader, paste Terrifying Cookies shader beneath the main function for now and have a closer look at it. You'll see it's not that complicated to read. First we see a sampler 2D texture 0 in the header. This seems to be the sampler 2D, or let's just call it texture, for this fragment shader. In the introduction video I mentioned that every texture passed into a fragment shader is of the data type sampler 2D. And in GMS/GLSL, the first texture is passed in automatically and is called GM-based texture. So we already got that covered and we won't need this line here. Then there's the main function. Looks like in HLSL the main function of the fragment shader is a float 4. It's easy to guess that a float 4 is the same as a vec4 in GLSL. And the main function receives a float2 or vec2 text chord 0. Now this has to be something like VV text chord in GLSL, doesn't it? So I think we got that covered in the header of our GLSL fragment shader already. Now let's just copy the content of the main function to our GLSL main function, just above the glfrag color line, and comment out the HLSL version. Now when I analyzed this code the first time, I kept getting a compile error and finding the error drove me nuts. I wrote the /* to comment out, but didn't do the */ in the end. And while GML accepts that, GLSL doesn't. So make sure you end the commented block with */. Now inside the main function we see a float 3 or vec3, color in and color out. The color out will probably be something like our GLFrag color, something temporary. Either way, we won't need it right now, and so I'll remove it. And the color in is probably just our VV color, and thus we won't need this either. So let's remove that line completely for now. The color in line looks very familiar. Let's quickly split our GLSL GLFrag color line and compare. This is practically the same. We grab the pixel color of the texture, texture 0 or GM-based texture, at the texture coordinates uv.xy or vv text code by using the function text2d or texture2d and store the color in a variable. So we can delete the float3 line and keep our base color line. Now to the next line. The comment says convert to linear space, probably not necessary since I totally destroy the color space later anyway. Okay, so color in is color in to the power of 0.45. This should look familiar if you did the tutorial video on brightness, contrast and saturation. This is a gamma correction. The F in 0.45F means it's a float. In GLSL we can remove the F or leave it there. I think it doesn't matter. I'll remove it because I'm not used to the Fs in floats, but for now let's just keep the rest of the line. It actually looks good, although by now I know it doesn't, but you'll see that later. The next line looks very familiar again. The comment reads, initialize the black and white color to the average color value, not 100% correct, but works decently. Float3 BW color is the dot product of colorin.rgb and 1.f.xxx times a third. Now I'm not sure what exactly 1.f.xxx does, but I guess it's constructing a float3 with all components set to 1. So in GLSL this would be vec3 1. So let's just replace it. Now this has to be the grayscale conversion. He's not using an NTSC or sRGB conversion, so we'll stick to that, but we'll just move the conversion into the dot product by constructing a vec3 with 0.333 and remove the tail of the line. And just to stick to the naming I'm used to, I'll name the variable gray. Now it seems to me that HLSL is automatically converting this to a float3 by defining BW color as float3. This wouldn't work in GLSL because, as we learned in previous tutorials, the result of a dot product is just a float. I'll define our gray variable as float for now. Now the next line. The comment reads, calculate the weight of the red color. Smooth step is a function that creates a quadratic interpolation between 0 and 1 using the first argument as the minimum value, the second as maximum value, and the third as interpolation value. Result is clamped to be 0 and 1. I just picked those constants because they looked decent in the image. So the line reads, float weight is smooth step with value 1 set to 0.1, second value set to 0.25, and the value to compare is the red channel of the pixel minus BW color. Let's quickly change that to our variables. So color in R is base color R and BW color is gray. And I'm removing the Fs because I'm not used to them. Now it's good we defined gray as float because GLSL would most likely not accept a vec3 here. But now this should work already. So basecol.r minus gray is the value to compare. Means we're interested if the red value is larger than the average value. So Terrifying Cookie begins working on the red color part of the Sin City shader. Value 1 is 0.1. So if the red channel is less than the luminance of the color or only a bit above it, 0.1 above it, smooth step will return 0 to the variable called weight. Value 2 is 0.25, so if the red channel is 0.25 or more above the luminance of the color, smooth step will return 1. and for everything in between, smooth step will return an interpolated value between 0 and 1. You can tell by the way this works and by the name of the variable weight that this will be used to mix colors. On to the next line then. The comment reads, mess with the color space of black and white, again arbitrary constants. And the line reads, black and white color is black and white color times 1.1 to the power of 2. Let's just replace the variable names again. Gray is power gray times 1.1, 2.0. So he's increasing contrast by 1.1 and then messing with gamma again. Let's just leave that line as it is. And the next line, interpolate between black and white and red based on the weight. And the line reads, color out is lerp from black and white color to color in times float 3 with 1.1, 0.5, 0.5 by the amount of weight. Let's rewrite this line to this. Base color.rgb is mix of gray and base color.rgb times vec3 1.1, 0.5, 0.5 weight. So we already know the weight is based on how much the red channel is higher than the luminance. So whenever red is not overrepresented, the mix function returns the gray value. But if there's a lot more red in the pixel, the mix will return the color value. And by multiplying with vec3 1.1, 0.5, 0.5, the values of green and blue are reduced to further push the red. This should darken the color a bit, but we'll see how those constants work in a later step of this tutorial. Now the last line. The comment reads, pow, convert back to gamma space. And the line reads, return, color out with an alpha 1 to the power of 2.2. Let's rewrite this again. It's obviously the line where in GLSL the GL frag color is set. So the line should be something like this. GL frag color is VV color times pow base col 2.2. So it's another gamma correction, and according to the comment, Terrifying Cookie is doing this to revert the gamma correction he did earlier with the power of 0.45. Now GLSL will not be happy with this code yet, but let's find out where by just running the program. By the way, if anyone knows if I can tell GMS2 to just compile the shader code and return errors, I'd really like to know. So please leave a comment if you do. Now the first error was probably obvious to everyone watching this tutorial. I forgot to replace color in with base col in several locations, so let's fix this. The second error seems to be in the power function and not so obvious. If we multiply, divide, add or subtract vectors in floats, GLSL automatically calculates each component with that float and returns a vector. However, inside the power function, both values need to be of the same data type. So we can fix this by constructing a vec3 with all components set to 0.45. Now we still got some errors left. One is in the GL frag color line and is the same problem as before, because the values inside the power function need to be of the same data type. But it's a little bit more complicated to solve because base col is a vec4 and I don't want to apply the power 2.2 to the alpha channel. So we need to create a vec4 from that power function and base col alpha, and we need to construct the 2.2 as vec3 again. And hopefully the last error seems to be in the mix line, and it's again the same problem as with the power function. GLSL expects the first two arguments to be of the same data type, so all we need to do is construct a vec3 from gray. Now let's run this again and see what happens. And it works quite nicely already. Now one thing I was curious about was how it looks without the two gamma corrections at the beginning of the shader and at the end. Because in the comments, Terrifying Cookie mentioned he's not sure if it's necessary. So let's remove and change those lines and run again. It seems like it makes quite a difference. As we learned in the brightness, contrast, saturation tutorial, gamma correction also affects the contrast of an image. And we also learned how contrast affects the saturation. And since this shade is based on the saturation of red, the gamma correction at the start affects what pixels become red. The gamma correction at the end is probably just reverting the brightness and contrasting effects, but it will not change what pixels get red anymore. But I agree with Terrifying Cookie's comment. I'm not sure if it's necessary to do it this way, but I like how those two lines work together, so I'm going to add them back in. Now that the code is working, I'd like to see what those constants do. First I'll need some more images to compare. So I'll go to the test room and add the object several more times, and in the creation code of each I'll set a different sprite to sprite 1. Just search the internet for images with some strong reds in them. And now I want to find out what some of those constants do or how they affect the final image. But before I do that, I want to reduce the comments a bit for more readability. At first I'm mainly interested in the two smooth step limits, so I'll create two uniforms, uniform float red threshold min and uniform float red threshold range, and replace the constants with those uniforms. I want to test what happens if the min value increases and what happens if the range of the max value increases. So I'll set the uniforms up to pass in values from 0 to 0.5, so together they will never get below 0 or above 1. Now I need to get and set those uniforms in the object. So in create event I set the handler uRed threshold min for the uniform red threshold min, and the handler uRed threshold range for the uniform red threshold range. And in draw event I set the two uniforms by using two global sliders of the base project. If you're not using the base project, you can either set constants and run the program multiple times or quickly create a slider or tween of your own. I'm going to set the uniform uRed threshold min to global.slider1 times 0.5. And the uniform red threshold range to slider 2 times 0.5. Both sliders return a value from 0 to 1, and so this code will pass values from 0 to 0.5 to the two uniforms. So let's run this and test those uniforms. Now this can't be right, not what I expected. Looks like I made a mistake in the fragment shader. Of course I need to add the threshold range to the threshold min to make this work properly. Now we can see what happens. So the threshold minimum determines how far red needs to be above the luminance to stay red. And the threshold range determines how far that threshold spreads. I think I like the threshold range to be at slider position 0.4, which would be a value of 0.2 since I multiplied the slider by 0.5. So I think I'll set this up as a constant for now. And as for the threshold minimum, it seems somewhere from slider position 0.2 to 0.6 looks good. So I'll narrow the range going from 0.1 to 0.3. So for threshold min, it would be slider times 0.2 plus 0.1. And for threshold range, it's just a constant 0.2. Now I want to look at the vec3 in the mix function. This seems to be some kind of saturation, so let's replace the 1.1 with a uniform red strength. uniform float red strength. So in create event, I'll add another handler, uRedStrength, for the uniform red strength. And in draw event, set the uniform to global.slider2 times 2. So let's run this again and see how this uniform now affects the reds. And it's different than I imagined. I thought it would be some saturation level, but it turns out it's more like a brightness. But it seems I like it most at slider position 0.5, which is just 1. So let's set the uniform to a constant 1. Now I'd like to test what happens if I rewrite the contrast line to something I'm more familiar with. So gray is gray minus 0.5 times contrast plus 0.5. This means I need another uniform float contrast. In create event, I'll set the handler uContrast for the uniform contrast. And in draw event, I set the uniform to global.slider2 times 4 plus 1 to get normal to extreme contrast. Let's see what happens. Now the line we replaced was not only changing contrast, it was also changing brightness by removing the gamma correction, and now everything is a bit too bright. Now again I would like to remove those two other gamma lines and see how that looks. And now everything is a bit too dark, and the contrast level pulls the luminance down, or at least it seems to. But what you probably could not see in the video were some speckles in the red that were bothering me, and those are gone now. So I decide to stick to this route and add brightness. I'm quickly adding a constant brightness modifier to the output color to see what happens. And of course this adds brightness to the reds as well. I do like the effect, but it's not what I'm going for right now. So I need to find a way to add brightness without affecting the reds. Let's try in our contrast line and run the program again. That looks more like it. So let's use a uniform for brightness here and define the uniform in the header. Uniform float brightness. In create event, we need to set another handler, uBrightness, for the uniform brightness. And in draw event, we'll set brightness to slider 3 times 2 minus 1. So the slider will pass values from -1 to 1. And let's run the program once more. Yeah, I like how that works. I think I'm happy with this shader now. We now got an understanding on how it works and how the different lines change the results. But if you feel the gamma version was better than the contrast and brightness version, feel free to revert to those changes. All you need to do is remove the contrast brightness line and the two uniforms, and remove the comments from the 3 gamma lines. Now if you implement this shade in a game, you can use the sliders to find settings that work best for your game and then replace the uniforms with hard-coded values. Now one last remark on this type of effect. You could also make a shader which pops a color based on its hue, but converting RGB to HSV is already a complicated thing to calculate, and it will cost a little performance. And even a gray color still has a hue, so you'd also have to check for saturation and maybe for luminance as well to decide which colors to pop. But if you want to try that, the basic maths would be similar as with a simple pop red shader we just created. You just need to Google a shader code for RGB to HSV or RGB to HSL. If you get a nice shader, I'm very interested in seeing the result and the code. Please post it somewhere and leave a link in the comments. So that's it for this tutorial. I hope you enjoyed this video. I think I'll show one last shader, a day-night cycle shader, before moving on to coordinate systems. But I haven't decided on that yet. Until next time.